Well, welcome. In this screencast, we're going to take a look at one of the common ways to approximate the value of a definite integral using a shape you're familiar with from your youth, trapezoids. So let's consider the following. Let's pretend that you have some function f of x on some interval from a to b. And you want to find the area underneath the curve. You want a good approximation for the integral from a to b of f of x dx. Well, the thought is that you break this interval up into a variety of partition points. Here's the first one, here's the second one, and the third, and so on. You can pick any number that you want. This is the seventh one. Traditionally, we call this the 0th one. And so you draw these vertical lines to the curve. And so the shapes that you get are trapezoids. Each of these shapes is a trapezoid. And the areas of the trapezoids roughly approximate the area under the curve. Well, what do we know? We know that the area of a trapezoid is half the height times the sum of the bases. And so in this case, the integral is approximately, well, this trapezoid right here, half the height, this is the height. This is the height of the trapezoid. The height of the trapezoid is half the change in x. And then the sum of the bases, well, these are the bases. These are the bases. F of x0 plus f of x1. And then the same thing happens for this trapezoid, delta x over 2 times f of x1 plus f of x2, and so on, until the very last one has an f of whatever the n minus 1th is, and then whatever the last one is. So what ends up happening? The integral from a to b of f of x dx is approximately, well, every one of these terms has a delta x over 2. Let's use that. And then there's an f of x0, there's an f of x1, and then another f of x1, and then there's an f of x2 and another f of x2, and then there keeps on being two f of x's until there's two f of the next to last one and one f of the end. This is the trapezoidal rule. It is the trapezoidal approximation of a definite integral. So what does that look like? Approximate the integral from 0 to 2 of x squared dx with the trapezoidal rule for trapezoids. For trapezoids means that our cut points are at 0.5 and 1 and 1.5. And the trapezoidal rule says that the integral from 0 to 2 of x squared dx is approximately delta x over 2 times a y value, 2 of those, 2 of those, 2 of those, and a y value. How do we find the y values? Well, the y values are what we get when we substitute this into the function, this into the function, this into the function, this into the function, this into the function. So that's 0, a fourth, 1, 9/4, and 2 squared is 4. 0 squared, 0.5 squared, 1 squared, 1.5 squared, 2 squared. What's delta x? Delta x is this distance. That's 0.5. And the calculator does the work for us, and the calculator tells us that that's 2.75. It's pretty close to the actual retail price. I mean, that's pretty close. It's a little bit big, but it's pretty close. Let's approximate the integral from 0 to pi of sine x dx with the trapezoidal rule with 4 trapezoids. Again, that's this region, 4 little trapezoids. So this happens at pi over 2, so this must happen at pi over 4, and this must happen at 3 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. And the integral from 0 to pi of sine x dx is approximately the change in x over 2 times y value, 2 of those, 2 of those, 2 of those, y value. The sine of 0 is 0. The sine of pi is 0. The sine of pi over 2 is 1. And then we got to remember what the sine of pi over 4 is, what the sine of 3 pi over 4 is. They're the same, and that's radical 2 over 2. What's the change in x? It's this distance, and that distance is pi over 4. So this is pi over 8 times 2 plus 2 radical 2. Is that good? Actually, it is pretty good. If you take the decimal approximation of this and the actual value of that, it's pretty close. It's pretty close. So one might wonder, how good is the trapezoidal rule? Like, how good is it really? And here's how we know how good it is. Let capital M be an upper bound for the absolute value of f double prime on AB. Then the error relating to the trapezoidal rule is less than or equal to that number m times b minus a cubed over 12n squared. What? What? Well, let's go back here a moment. How good is this approximation? The error relating to the trapezoidal rule is less than or equal to capital M times b minus a cubed over, oh really? Over 12n squared. Well, in this case, b minus a cubed 12n squared. What's m? M is the biggest that f double prime could possibly be. Well, this is f. F prime is cosine x. F double prime is negative sine x. So the most that negative sine x could be between 0 and pi, the farthest away that could be from the axis is 1. It's 1. And so this is pi cubed over 192. This is about 30 over 192. This is about 1/6. So this number, whatever it is within about 1/6 of the actual area. How do we make our approximation better? We use more subintervals because that makes the denominator bigger. That's a way to make the approximation better, and that's really a good takeaway to have from this. We can make our approximations better by making the number of subintervals bigger. Okay? Hope this is helpful to you. See you in class.